Okay, we stopped at 1.3 last week, so let's start. Please mute all your microphone. Gigi, please mute your microphone. Okay, limits at infinity. So limits is at infinity is when x tends to either plus infinity or x tends to negative infinity. We want to uh, investigate the behavior of the function whenever it is at, I mean, approaching infinity or negative infinity. Okay. Like here we have a reciprocal function 1 over x. Okay. So limit at infinity and horizontal asymptotes. I think last week we have discussed about vertical asymptotes, right? Okay. Um, so for these reciprocal functions, we note that it has horizontal asymptotes as well as vertical asymptotes. Okay? So if you look at here, okay, so this is the horizontal asymptotes. And this line here, this y axis here is the vertical asymptote. Okay, so horizontal asymptotes is when we have x approaching infinity or x approaching negative infinity, and the function is somehow getting closer to a line. And that line is called horizontal asymptotes. It's never touched this line, this y equal to 0 or x-axis. It's never touched this line here, y equal to 0, the line y equal to 0, or it is also called x-axis, but it's getting closer. It's getting closer to this line. Okay, whenever x is approaching, um, whenever x is approaching infinity. Okay, so that's why we can write it as the limit x tends to negative infinity to this side here. It's getting closer to negative infinity. Okay. For the function 1 over x, okay. If you note here, the graph is getting closer to 0. Okay. So that's why here we have 0. So this is to indicate that y is equal to 0 is the horizontal asymptotes. Okay. And then we also have the limit for 1 over x as x tends to plus infinity for the right hand side here. It's also getting closer to 0, and it's not gonna touch the line y equal to 0, but it's getting closer to y equal to 0. So that's why we have this one. So both of these statements here indicates that it has a horizontal asymptotes at y equal to 0. Okay, and then you can also do it in terms of table form. Okay, like if you choose -1, -10, -100, and negative of a big a very big number, okay, and check the values of that functions, okay, to see the behavior of it, okay. So this is in the case of when you don't know on the graph of the function. But for the 1 over x, we know that this is how the shape of the function, then it is fine, okay. And then here as well we have functions, okay. And here if you look at uh, at around here closely, with x approaching infinity, somehow the function is getting closer to a line, okay. And this line here is called horizontal asymptotes, okay. And then this one as well, when x is approaching so here limit fx, okay, fx is the function, as x approaching is getting closer to negative infinity, okay, is this side here. This is as x tends to plus infinity, and this is for x tends to negative infinity. This one, it is getting closer to y, so it is called it is equal to L, sorry, okay, y equal to L, okay. And then let's look at this example 2. If you look at this graph here, so this is the graph of arctangent of x, okay. Arctangent of x, as x tends to plus infinity for the right hand side, okay, x tends to plus infinity, the limit of it is approaching pi over 2. So this one is the horizontal asymptote. And as x approaching negative infinity, the function, the arctangent of x, is approaching negative pi over 2. So this line here is also called horizontal asymptote. Okay, tutup pintu. Okay, and then we have a function fx equal to 1 plus 1 over x to the power of x. Okay, for example 3. And the graph is given in figure 1.3.4. Okay. And if you look at here, there's a line, this red line here, which is in between 2 and 3. And this is actually E. E, if you press your calculator, it will give you 2.71 something. So it is a constant. Okay. Which is obviously located between 2 and 3, okay. As x tends to plus infinity, okay, the function is getting closer to this line, which is equal to E. It's the same for the left hand side. As x tends to negative infinity, is getting closer to E, okay. So this line y equal to E is the horizontal asymptotes for f in both the positive and negative directions, okay. So it's not difficult for you to understand the horizontal and vertical asymptotes. And then for the vertical asymptotes, for the revision, it is for the vertical lines, okay. But somehow the function is never touch the vertical line. So like in our reciprocal function, as x tends to 0, if you look at here, limit f as x tends to 0 from the right hand side, so it means that x tends to 0 positive, okay, it is equal to what? It is equal to plus infinity, isn't it? It's getting closer to it will be a very big number here over here. So so x equal to 0 will be the vertical asymptotes. So this is the vertical asymptotes. Okay, vertical asymptotes. It's the same for the limit of f as x tends to 0 from the left hand side. It will be negative infinity. So the limit of f as x tends to 0 from the left hand side, 0 super index negative, this one will give you negative infinity. Okay, so x equal to 0 will be the vertical asymptote. Okay, so that's the difference between horizontal and vertical asymptotes. Okay, and here we have several graphs for the polynomials. This is the graph of a linear function. This is quadratic, and this is a cubic function, and somehow this is for a graph for a function of order 4. If you look at closely, the graph of order 4 is somehow similar to the graph of order 2. Okay, but then it's if you look at the shape of the graph, it's somehow getting slimmer. It's getting slimmer compared to when we have y equal to x to the power of 2. So this will continue. So the shape of the graph for y equal to x squared, y equal to x to the power of 4, y equal to x to the power of 6, y equal to x to the power of 8, they are all similar. Okay? What's the difference is just the shape of it. The shape is similar, but then how slim the graph is will be different. Okay, so these are one families of similar graph, and then we also have similar graph for y equal to x square x cube. Okay, y equal to x to the power of 5, y equal to x to the power of 7, and so on. So for the odd order, they are the same. For the even numbers, for the even orders, they are also similar. Okay, so we expect that the graph for y equal to x to the power of 5 will be something like this. Will be similar to y equal to x to the power of 3. So the shape will be something like that. Okay, is it okay? Okay, good. And then based on this shape of graph, we can actually predict the limits. So if you look at here, 2x to the power of 5, as I said, it will be similar to this one, isn't it? Will be similar to this graph. Okay, so what happened as x tends to plus infinity for this side? It will be plus infinity. Okay, it will be plus infinity. It will be plus infinity. And what about when we have x tends to negative infinity for this side? It will be negative infinity. Okay, what about this one? Limit x tends to 4. Sorry, limit x to the power of 4 as x tends to plus infinity is going up, isn't it? So it is plus infinity. Limit x to the power of 4 as x tends to negative infinity, this one is going up as well, so it is also plus infinity. Okay, so it's similar to this one. This one is plus infinity as well, this is plus infinity. Okay. But this one, for x to the power of 7, so limit x to the power of 7 as x tends to plus infinity, this one will be plus infinity. Limit x to the power of 7 as x tends to negative infinity, it will be negative infinity, because it's similar to this shape. Okay. And then x to the power of 6, which one is similar? This one, isn't it? And this one. Okay, both of them. So x to the power of 6, as x tends to plus infinity, it will be plus infinity, but because of this sign here, you have this sign negative, so that's why it will be negative. Okay, because the original one for 7x to the power of 6 is plus infinity, it's going up, okay. And then because of this sign here, we still have to write the negative. And then this one as well, 7x to the power of 6, it will be plus infinity, but because of this sign, it will be negative infinity. Okay. Okay, that's it about the graph. Okay, let's look at the example. Okay, for the example, we have combinations of lots of power here. 7x to the power of 5 minus 4x to the power of 3 plus 2x minus 9. Okay, the key here is to find the highest order. Okay, you find the highest order because the highest order will be dominant. Okay, will be dominant. We can neglect the lower order. Okay, because if x tends to plus infinity, it will be if you have if you have y equal to x and y equal to x squared, which one will contribute more if you have x tends to plus infinity? Obviously for x obviously for x to the power of 2, right? So let's say you have y equal to x squared and y equal to x. Okay, this one the same. Let's say you have a very uh, a very big number. So let's say 1000. Okay, 1000 and 1000 squared. Which one will be much bigger than another? So obviously 1000 squared is much bigger than 1000. It's the same if you have y equal to x to the power of 7. Okay, 1000 to the power of 7 is much bigger than 1000 squared. So that's why you can always neglect those with lower order and just consider the higher order. So in this case, if you have 7x to the power of 5 minus 4x to the power of 3 plus 2x minus 9, you just have to consider the highest order. In this case, it is 7x to the power of 5. So that's why we can write it as the limit x tends to negative infinity for the function 7x to the power of 5. Okay, and 7x to the power of 5, we know that the shape will be somewhat similar to this one. Okay, so as x tends to negative infinity, it will be going down. It will be negative infinity. Okay, and then for this one, for x to the power of 8, this is the highest order. Okay, x to the power of 8 here, the graph will looks like this. Okay, will looks like this. X to the power of 8, as x tends to negative infinity, it will be this side. So it will be it will be positive infinity. But because of this sign here, this negative sign will contribute also to the final solution. Okay, the original one will be plus infinity, but because of the sign, it will contribute to the final answer, which is negative infinity. So any question? Anyone? Okay, so I hope it is clear. Okay, and then we have rational functions. So rational functions is something that we have to be careful with. because it's not as simple as polynomial. Okay. For the rational function, we have numerator and denominator. The numerator is the upper parts and denominator is the lower part. Okay, so this is numerator and this is denominator. Okay, and then if you substitute in this function here, x tends to infinity, if you substitute, you will actually get infinity over infinity. So I think I've mentioned this last week. Whenever you have infinity over infinity or 0 over 0, you can always use L'Hopital rule. Okay? I hope you still remember that. Okay, you have this L'Hopital rule. It's a very famous rule here and it's a very useful rule. So when you have infinity over infinity, you can always apply L'Hopital rule. But if you don't get infinity over infinity, then you cannot apply L'Hopital rule. Okay. So in this case, you can apply L'Hopital rule. Okay. So the limit of 3x plus 5 over 6x minus 8, x tends to plus infinity. Okay, so obviously this is infinity over infinity. So L'Hopital rule says that you can differentiate each of the parts here, numerator and denominator. This one is equal to the derivative of the upper parts, which is 3, divided by the derivative of the lower parts, which is 6. And x tends to plus infinity, okay? So the answer, this is just a constant, so that the answer will be just 1/2. Okay, so it's the same as the solution given in this example 7 here, but somehow what they do is different methods. Okay, they use division by the highest order of the denominator. I think you have learned this in your matriculation, right? I hope so. Okay. So this is another method which can also be applied, which is you divide with the highest order of the denominator. Highest order of denominator. Okay. So the highest order of the denominator is this one, 6x minus 8. So you divide with x. Okay. Divide everything with x, and then you take the limit as x tends to infinity. For 8 divided by x, obviously it will give you 0 for this one. 5 divided by x will give you 0. 8 divided by x will also give you 0. 8 divided by something which is a very big number will somehow give you a number which is approaching 0. So that's why this one is approaching 0. Okay, these two will approaching 0. So that's why you got 1/2. Okay. Okay, and then let's look at the next example here. 4x squared minus x divided by 2x cubed minus 5. Okay. So this one, if you substitute x tends to negative infinity, then what will you have? For the upper parts, you just have to consider the highest order. Okay, you don't have to consider this negative x, because x squared is more dominant than x. Okay, so x squared, the graph will be something like this. Okay, it is a quadratic. And then as x tends to negative infinity, this one will apply that is going to plus infinity. Okay, and then what about the other side? Sorry, the lower parts, which is 2x cubed. Okay, So the graph will be something like this. Okay, as x tends to negative infinity for this side here, 2x cubed, 2x cubed, as x tends to infinity, it will be negative infinity. So negative plus infinity, you divide with negative infinity, it will be what? It will be a negative infinity divided by infinity, isn't it? So the negative is okay. You can still apply the L'Hopital rule. It doesn't matter. So it is either 0 over 0 of infinity over infinity or negative infinity over infinity. It is fine. Okay, you can still apply the L'Hopital rule. So in order to apply the L'Hopital rule, you differentiate the upper parts. Okay, so this one 8x, okay, as x tends to negative infinity, the lower parts will be what? 6x. We left negative 1, sorry, negative 1. Okay, 6x squared. 6x squared. And then you substitute once again, you will still get infinity over infinity, right? Isn't it? Okay, and then you apply the L'Hopital rule once again. Okay, and see what gonna happen. So limit x tends to negative infinity. You differentiate the upper parts, you get 8. The lower part will give you 12x. Okay, once you substitute, it will give you 0 because 8 divided by infinity. Okay, sorry, this is negative, right? Okay, negative infinity. Okay, 8 divided by something, a negatively large number, it will give you 0. So the answer will be 0. Okay, but somehow the methods that is used in this book is by dividing the highest order of the denominator. You can also apply these methods. Okay, I'm sure you have learned this during matriculation. But the L'Hopital rule is a rule that I've always used because it's a very useful method, and it's shorter. I mean the calculations and the derivation is even shorter than the methods which is used in this book, shown in this book. Okay. Okay, and then we have for solution B. What is this? Okay, okay, for this one, for the second example. Okay, for the second example, 5x to the power of 3 minus 2x squared plus 1 divided by 1 minus 3x is the same. It will give you infinity over infinity. You just have to apply a L'Hopital rule. Can you please do it? I give you 5 minutes and see if you can get the answer or not. Okay, I'm giving you 5 minutes. Okay, so did you get the answer? Okay, any problem? No? Can we skip? Okay, good. And then we have what? Example 9. Example 9 is also the same problem. You can still apply L'Hopital rule here. You can still apply L'Hopital rule because it will give you infinity over infinity. And then straight away you can use L'Hopital rule. You differentiate the upper parts, it will give you 3. The lower part will give you 6. So the answer will be 1/2. Okay? So what about this one, example 10? Example 10 is when we are dealing with radical. Radical is this square root sign. Okay? So it could be cube root, it could be square root. Okay? And this one somehow it's dealing with the square root. Square root of x squared plus 2 divided by 3x minus 6. Okay? So whenever you have this kind of expressions, you have to consider this absolute value of x. Okay? So absolute value of x is always positive. So the graph of absolute value of x will be something like this. Okay? It's like this. If we have y equal to x, it will be like this one. Okay? It will intersect at 0, 0. Okay? It's just one line. It should be just one line. Okay, let's redraw. Okay, so this is good. So y and this is x. So this is when we have y equal to x, and this is when we have y equal to the absolute value of x. Okay, if you look at this graph, you know that we can always summarize this or write it so that it's segregated into 3 parts. One is, so y here, it is equal to x when x is greater than 0. Okay, for this side here. And then you have y equal to 0. So this is y equal to 0 when x is equal to 0. And then you will have y equal to negative of x when x is less than 0. So this is y equal to absolute value of x. Okay? Is it okay? Okay, good. The other way, sorry. In expressing y equal to absolute value of x is this one, is square root of x squared. Okay, why is that? It is because if you look at the graph, y equal to the absolute value of x is always positive. It is always positive, and then what is the behavior of square root of x squared? Is it always positive? So let's say you have x equal to 2. 2 squared, 4. Square root of 4, it is equal to 2. Okay, so let's say what happens if x is negative? So negative 2. Negative 2 squared is 4. Square root of 4 is also equal to 2. So square root of x squared is also equal to the absolute value of x. It's the same. Okay, so we can also equate absolute value of x as this one. Okay, but then please be careful when x is positive and x is negative. Okay, but whatever it is, let's look at this one first for a. Okay, So square root of x squared plus 2, you want to divide with the highest order of denominator. We cannot use L'Hopital rule in this case. We want to divide with the highest order of denominator. In this case, the highest order of denominator is this one, 3x. So you want to divide with x. But instead, because this is involving radical, you have to divide with the absolute value of x. Okay? So you divide with the absolute value of x, both sides, okay, for the numerator and denominator. But for the numerator, you have to change the absolute value of x so that it is in terms of square root of x squared. Because you want to combine and cancel out, okay? So this one, square root of x squared, after you get, you combine this, you can cancel out the first term here. It will be 1 plus 2 divided by x squared. Okay, it's already under the square root sign. And for this one, it is fine. For the denominator, it is fine. It doesn't involve radical. Okay, and for the numerator, the limit expression can be moved inside the radical sign. And after that, you act on each of the expression. You can segregate so that it acts on each of the expression. So limit 1 and this one, 2 limit 1 over x squared. Okay, 1 over x squared, as x tends to infinity, it will somehow give you 0. So this part here will be 0. And this one as well. 1 over x, as x tends to plus infinity, will be 0 as well. This one, it doesn't change because this is just a constant. Limit 1, x tends to infinity, for 1, it is fine, it will be just 1. Limit 3, as x tends to plus infinity, it is okay, will be 3. Okay, and then you simplify this, you will get 1 plus 2 multiplied with 0 divided by 3 minus 6 multiplied with 0. So the answer will be 1/3. Okay, the answer will be 1/3. Okay, for B, there's a difference between A and B because of x tends to plus infinity for A, but for B, it is x tends to negative infinity. Okay, that's the difference here. Okay, so the difference is this one. X tends to negative infinity. Okay, so, okay, it's the same like before. We have to divide with the absolute value of x. Okay, we have to divide both sides with the absolute value of x, and then we replace the absolute value of x with the square root of x squared. Okay, for the numerator, because we want to combine with the original expression. But for the denominator, absolute value of x, as x tends to negative infinity, if you look at this function here, as x less than 0, for this side here, it means that for x tends to negative infinity, the y will be negative x. Okay, the absolute value of x will be negative of x for x less than 0. Okay, so this is the y, is the same as absolute value of x. It is equal to negative of x. So you replace this absolute value of x with negative x. Okay, because for this side, it is for x less than 0. It is for x tends to negative infinity. Okay, so it is for it will, you have to write negative x here, and then you do manipulation, calculation here, mathematical manipulation here, and you got negative 1/3. Okay, instead of positive, you somehow got negative. Okay, any questions about this? So the only difference is just you replace the absolute value of x here with negative x, because you have absolute value of x is equal to negative x when you have x less than 0. So this is by definition. Okay, by definition of the absolute value. Okay. Okay, now example 11. Okay. For example 11, limit x tends to plus infinity, square root of x to the power of 6 plus 5 minus x to the power of 3. Okay, so in order to cancel out the radical sign, you have to multiply with the conjugate. Okay, I hope you still remember the conjugate. Conjugate means it's the same expression but somehow you have plus here. If here you have minus, then it will be plus. If here you have a plus, then it will be minus. Okay, so it will be different in terms of sign. Okay, so here since it has negative, this one will be positive. So you multiply with the same expression but different sign. Okay, it means that you have to multiply with the conjugate. So this is called conjugate. Okay, and then you multiply in order to so this methods on multiplying with the conjugate is because you want to get rid of the radical sign. Okay, so somehow you get x to the power of 6 plus 5 minus x to the power of 6. Okay, actually this is from a minus b multiply with a plus b, it will be a squared minus b squared. Okay, so your a here, so this is minus. Your a here will be square root of x to the power of 6 plus 5. And then your b is x to the power of 3. You multiply with this one. So obviously you will get x to the power of 6 plus 5. Okay, the radical sign will there won't be any more. There won't be any more radical sign. Okay, minus b squared. So x cubed to the power of 2, it will give you x to the power of 6. Okay, and then this one, it can cancel out. X to the power of 6 cancel out. What is left will be 5. Okay, and then this one, it stays. It stays. As x tends to plus infinity for the numerator is already doesn't involve any radical sign, but we still have the radical sign for the denominator. For the denominator, it is fine. Okay, if you substitute infinity here, it will give you infinity. Is it 5 infinity plus 5 plus infinity? So 5 divided by infinity, it will straight away give you 0. Will straight away give you 0. You don't have to divide with the highest order of the denominator. But then you have to be careful. I've always suggest you to try substitute. What happen if you have a very big number, positively big number? In this case, x tends to plus infinity, so it means that a positively big number. So what happen if you have, let's say, you substitute 1000 to the power of 6 plus 5 plus 1000 to the power of 3. Okay, and see what your calculator give. Is it a positive of a big number? Is it 0 or what? Okay, or is it negative of a big number? Something like that. Okay, please check with the calculator before you can make conclusion. But then it's enough. From here, you know that it's going to give you something like infinity or negative infinity. You have to be sure with the calculator. So from here it will be 5 divided by a big number, then it will give you 0. Okay? Any question? Anyone want to say something? Or something which is not clear that you want to ask? Okay? Okay, good. It's the same for the next example here. What's the difference between both example? It's the same. What's the difference? I thought they're the same. Oh, the difference is this
X cube.
5x to the power of 3. Okay, for the 5x to the power of 3, okay, just it's the same methods like before. You have to multiply with the conjugate. So this is plus, because this is minus. This is the conjugate. Okay, you multiply with the conjugate both sides. Okay, because you want to get rid of the radical sign for the numerator. For the denominator, it is fine. Okay, and then 5x to the power of 3 divided by square root of x to the power of 6 plus 5x to the power of 3 plus x to the power of 3. If you substitute, it will somehow give you what? In this case, it will give you infinity over infinity. It will give you infinity over infinity. So you divide with the highest order of the denominator, x to the power of 3. Okay. You divide with x to the power of 6 for under the radical sign. Okay. Because square root of x to the power of 6 is actually equal to x to the power of 3. Okay. This one. So that's why for the denominator, you have to divide with x to the power of 6 under the radical sign. Okay. So what is left will be 1 plus 5x to the power of 3 divided by x to the power of 6. So you get 5x to the power of 3. Okay. And then plus x to the power of 3 here. Because you divide with x cubed. Okay, it will be 1. Okay, good. And then what? Okay, once you reach here, 5, which is fine. You substitute x tends to plus infinity. It will be 0 over here. So 1 plus 0 plus 1. So the answer will be 5 divided by 2. Okay. Anything want to ask? Is it clear? I hope it is clear. But I'm not sure how you can accept this English. Or is it difficult for you to understand? If it is difficult, then you have to tell me. Okay. And then we have an behavior of trigonometric, exponential, and logarithmic function. So this is for ln of x, and this is for e of x. Okay, so ln is when you have logarithmic function with the base e. So this is called ln of x. Okay, or you can always write ln of x. Okay, so the graph of exponent will be this one. So y is equal to the exponent, and then we know that the ln is just the inverse function for ln. So when we say inverse, it means that it's just reflection of the original graph y equal to ex about y equal to x. Okay, so you have a straight line y equal to x. The inverse function will be reflected to each other about this line y equal to x. So y equal to ex will be this graph, and y equal to ln of x will be this graph. Okay, and then if this is y equal to ex, and then this is the graph of y equal to e to the power of negative x. Okay, and if you want to find the end behavior of this function here, so the limit of ex as x tends to plus infinity will be what? Will be plus infinity. And then the limit of ex as x tends to negative infinity for this side, it will be what? It will be 0. It's getting closer to 0 but never reaches 0. So it means that y equal to 0 is the horizontal asymptotes. Is the horizontal asymptotes. Okay? And then you have what? You have this one. So this is y equal to ex, and this is y equal to negative ex. E to the power of negative x, as x tends to negative infinity, for this side it will be plus infinity. As x tends to plus infinity, it will be 0 because it's getting closer to 0, but not 0, but never reach 0. Okay, I think that's it. So let's continue. To definitions of the continuity. I think we have discussed this before. I've always expressed continuity with how we can walk along the graph. Okay, so like in this graph here, this figure 1.5.1, okay, if you yourself try to walk, so this is you, okay, we have a person here. You want to walk along this graph, you have to jump, okay, because there's hollow dots here. There's hollow dots. It makes this graph is not a continuous function, okay. So like this one as well. If you have to walk along this graph, you still have to jump whenever it reach this one. It's not continuous. It's continuous everywhere except at one point. This one as well. It's continuous everywhere else except at one point. There's one point that you have to jump. It's this one. If you try to walk along this graph, you somehow cannot reach to the other side. Okay, because you have to do the very long jump here in order to go to the other side. It's not possible because it's approaching plus infinity over here. It's not possible for you to jump. So it's not continuous. Okay, for this one as well. There's hollow dots here, and this is full dots. Okay, so for the definition, mathematically, the function f is undefined at C. Okay, for this one, for the first figure, the function f is undefined at C. That's why we have hollow dots. So that makes the graph not continuous. And then for the second graph, the limit from the left and the limit from the right, they does not exist. Why does not exist? Because they are not the same. One is approaching this side, this one here. So maybe this is maybe A, and another one is approaching B. Okay, another one is approaching B. Okay, and A and B, they are not the same. So that's why the limit does not exist. Okay, so this, whenever it doesn't exist, then it's not continuous as well. And then for this one, the limits is approaching plus infinity, and this one, the limit is approaching plus infinity as well. So the limit of f as x tends to c from the left is equal to plus infinity. Okay, the limit of f as x tends to c from the right is also plus infinity. Plus infinity means it does not exist. Okay, so the limit of f as x tends to c does not exist because we don't know what is the value of this plus infinity. So it does not exist. Okay, the value, the limit does not exist as x approaching c. Okay, but f of c is defined. It's defined over here. Maybe this is equal to d. So this is d. So f of c is equal to d. It is defined. Okay, and but somehow here f of c might be equal to d. F of c might be equal to d, which is this full dot. So this full dot is equal to d. Okay, but it is not equal to the limit. Okay, so this one might be equal to, let's say, b. So the limit of f as x tends to c from the left as well as from the right is equal to b. And the b is not equal to d. Okay, b is not equal to d. So that's why this function is not continuous. So the limit of f as x tends to c must be equal to f of b. Sorry, f of c. F of c. Okay. In order for the function to be continuous. So that's why we come to the conclusion that for the continuous function, it must satisfy these three conditions. So the first one is fc is defined. So fc is defined. So for the first graph, fc is not defined. So that's why we just have the hollow dots. So it does not continuous. F of x exists. Okay, so for this one, does it exist? No, because they are not the same. Left hand side, they are not the same. It means that it does not exist. For this one as well, it does not exist. Okay, it goes up to plus infinity for both sides. Okay, so it failed to be satisfying. It failed to satisfy the second condition. Okay, and then the limit of f as x tends to c is equal to f of c. Okay, so this one f of c is equal to d, but what about the limit? The limit is somehow equal to b. Our fc is equal to d. They are not equal, so that's why it is not continuous. So if it satisfies these three, then we say that it is continuous. So how do the graph of continuous functions looks like? It will look something like this in C. Okay, if you walk along the graph, you don't have to jump. So let's say for this one, f of, so this is g instead of f. So the limit of g, as x tends to, this is approaching 2 from left and from the right, they are the same, and it is equal to 4. So this is 4 here. It is equal to 4. Okay, this is limit lim. But what about f of 2? F of 2 is somehow equal to 3. F of 2 is somehow equal to 3. They are not the same. Okay, so that's why it is not continuous. And what about this one? This graph is not a continuous function is because f of 2 is not defined. F of 2 is not defined. Okay, so for the condition that we have list here, f of 2 is not defined, so it failed the first condition. And then for this one here, the limit of g as x tends to 2 and f of 2 they are not the same. So it failed the third one, the third condition here. But this one, it passed all the three conditions. The limit for the both sides, left and right, as x tends to 2, they are equal to f of 2, which is equal to 4. Okay? So this one is a continuous function. So this is the only continuous function that we have here. Okay? So any questions? Is it clear? Okay? Okay, good. Okay, now example 3. For what value of x is there a discontinuity in the graph? In the graph of x squared minus 5x plus 6, that is the denominator, and the numerator is x squared minus 9. So for the rational functions, you have to be careful with the denominator. Our denominator, so the denominator is the lower part. So this is called denominator, and this is numerator. Polynomial is fine. Polynomial is always continuous. But for rational function, we have to be careful, especially for the denominator, because the singularity is decided by the denominator. Okay, singularity is the point where the function fails to be continuous. Okay, so if you look at the denominator, our denominator is x squared minus 5x plus 6. Is there any points that makes the function equal to 0? Is there any points of x that makes x squared minus 5x plus 6 equal to 0? If you try to find the x here, you can use your calculator. I think your calculator can give this. Or maybe you can just factorize. Factorize x, I think 2 and 3, isn't it? 2 and 3, and then you have minus. So x equal to 2 and x equal to 3. Okay? So there's 2 points that you have to be careful with. So these 2 points are the points where the function failed to be continuous. Or in other words, it is the 2 singularities of the function. So if you look at the graph of the functions, you have a hollow dots here when x is equal to 3. So this is when x is equal to 3. You have a hollow dots. And then you have another point. This is a vertical asymptotes when x is equal to 2. It's not defined as well. The graph is not defined for this vertical asymptotes. And there's another point here. This is called singularity points, where the function failed to be defined. So that's why we have hollow dots. Okay? So this is how we have to be careful with whenever you have rational function. Okay. And then for the example 4, you have absolute value of x. So this is the definition of the absolute value of x. We have written it before. So it is equal to x if x is greater than 0. Absolute value of x is equal to 0 if x equal to 0, and it is equal to negative x if x is less than 0. Okay. And then the questions ask us to show that the absolute value of x is continuous everywhere. Okay, by graph, it will look something like this. By graph, it will look something like this. Something like this. If you walk along the graph, you don't have to jump at any of the points. Okay, you know that it is continuous, but how you explain it is you know that for this side here, it's just a polynomial. Absolute value of x is just a polynomial. And then for this one as well, negative x is just a polynomial. But something that we have to be careful is when the absolute value of x is equal to 0. So that is somewhere that we have to prove the continuity. Okay. What is we have to do is we have to prove that the limit of absolute value of x as x tends to 0 exists. It means that both sides of the limits give you the same value. So the limit of absolute value of x as x tends to 0 plus, it is equal to the limit of x as x tends to 0 negative. Okay, so both give you 0. This one x and this one negative x, both give you 0. It means that it's exists. It's exists. The limit of it exists, and somehow it is equal to this f of 0. F of 0 is equal to 0, and it is equal to the limit of fx as x tends to 0 from any side, from negative or positive. Okay, and they are equal to 0 as well. So since these two are equal, then we know that the absolute value of x is a continuous function. Okay. Okay, let's have like 5 minutes break before we start our next chapter. Okay. 5 minutes break. Okay, okay, next chapter, derivative. The tangent line and rate of change. Okay. Okay, I think I've mentioned before about the secant line and the tangent line. Okay, and then we want to discuss about the slope. The slope of the tangent line. The slope is keturunan in Bahasa Melayu. Okay, the slope of the tangent line. It is somehow be expressed as the limit of fx minus f of x naught divided by x minus x naught as x is approaching x naught. Okay. So f is f of x is the coordinates of y for q. Okay. So the q here, the coordinate of the q is equal to x, comma f of x. Okay. And then, so this is the coordinates. We have two coordinates. One is x, another one is y. Okay. So f of x is expressing for the coordinate of y. And then for p, the coordinate of p, which is a fixed point, the coordinate of it is x naught, comma, f of x naught. Okay. So this is how we get these two uh, functions, fx and f of x naught. It's dealing with the y coordinate of both of the points, P and Q. And then x and x naught is the x coordinate. X naught is the coordinate for P, and then the x here is the coordinate for Q. Okay, so I hope that is clear. And tangent. Okay, as the limit x tends to x naught. So we get the limit of x tends to x naught is because we know that our point Q is moving towards the point P. So if it move towards this point, so let's say you have Q here and this is P, we know that if it's moving toward P, means that our x, which is the coordinate of Q, is moving towards x naught. So that's why we have the limit x tends to x naught. We can also write the limit of the limit of fx approaching f of x naught. But normally, this limits is expressed in terms of x. Okay, so that's why we have limit x tends to x naught. It indicates that this q is somehow moving towards p. So this is the slope of the tangent. Okay, so the difference between the slope of the tangent and the slope of the secant is m secant is given by the same formula, except that we don't have this limit expression. So this one, m secant, will be fx minus f of x naught, okay, divide by x minus x naught. Okay, so this is for the m secant. Okay, now let's look at example 1. Use definition 2.1.1 to find an equation for the tangent line. Okay, in order to find the equation of the tangent line, obviously we have to first find the slope of the tangent line. Okay, after we get the slope, then we substitute in the equation of line in order to get the equation for the tangent line. Okay, and then in this example here, somehow it says that we have a parabola. Okay, parabola is a quadratic function, so y is equal to x squared. So this is y equal to x squared. At a point P11, Okay, so x naught is equal to 1 and f of x naught is also equal to 1. So the coordinate of this is P11. Okay, and then we have Q somewhere maybe over here. Then it will move towards this point P. Okay, and then we want to apply the previous formula. M tangent is the slope of the tangent. Limit x tends to 1 because our x naught is equal to 1. Fx minus f of x naught. X naught is equal to 1, so that's why f of 1. Divide by x minus 1. Okay. And then we substitute. If you substitute x equal to 1 here, you will have problem because the denominator will be 0. We don't want that. We have to simplify so that the denominator is cancelled out. Okay, so in order for us to simplify, we have to factorize x minus 1, x plus 1. Okay, and that's why we can cancel out the denominator. So x plus 1, and after that we substitute x tends to 1, it gives you 2. So this is the slope of the tangent line. It doesn't stop here because the questions not only ask you for the slope of the tangent line, but also the equation of the tangent line. Okay, so for the equation of the straight line, it is given by y minus y naught equal to m multiplied with x minus x naught. So this is equation of the straight line. So you already know m tangent. So this is 2. What about y naught? Y naught is equal to 1. X naught is also equal to 1. So this is 1, this is 1. Once you substitute, then you get y minus 1 equal to 2 multiplied with x minus 1. And then after you simplify and make y as the subject, you will get y equal to 2x minus 1. So this is the equation of the tangent line. Okay? This is the equation of the tangent line. Okay? That's it. It's not difficult. Okay, so this is one way to express the slope of the tangent line, but we have another way. The second formula is given by this one. This expressions is dealing with h. Okay, so for this case here, we denote h as x minus x naught. Okay, so the original one is this one, f of x minus f of x naught. Okay, f of x naught divide by x minus x naught, isn't it? And then we have here limit x tends to x naught. Okay. Okay, if you look at here, what happened if you express x minus x naught as another variable, which is h? As x tends to x naught, if x is moving toward x naught, our h will move towards 0. So here the limit can be written in terms of a h as the limit h tends to 0 because x is getting closer to x naught. Our h will getting closer to 0. And then x is equal to h plus x naught. Our x is equal to, you make x as the subject, it will be a h plus x naught. It will be h plus x naught. So that's why for this part here, it can be written as f of x naught plus plus h. And then for this one, for the second part, negative x naught stays because we want to get rid of x. And then you divide with x minus x naught. X minus x naught is h. So that's why you got this second formula. So the second formula is just the same as the first formula. You can use either one of it. It depends. Maybe some of the questions, it might be easier for you to use the first formula, but it could be that the second formula will be easier for you to use. It depends. So you have to know both of the formula. Okay. Let's look at example 2. Okay, compute the slope using formula 2. Formula 2 is dealing with h. So h tends to 0. So this one, f of x naught plus h minus f of x naught divided by h. Okay, f of 1 plus h, fx is equal to x squared. So f of 1 plus h will be 1 plus h squared. Okay, minus 1 squared because f of 1 is equal to 1 squared. Okay, you divide with h and then you simplify, you get this one. And then 1 can be cancelled out. What is left will be 2h plus h squared, and you can divide with h here. Okay, so the answer will be 2 plus h tends to 0. You substitute h tends to 0, you get 2. Okay, so this is the slope of the tangent line, which is the same with the example 1. So you can either use formula 1 or formula 2. Okay. Okay, and then we have example 3 here. Find an equation for the tangent line to the curve y equal to 2 divided by x at the point 2, 1 on the curve. So you have y equal to 2 divided by x, okay. And then somehow you have a point 2, 1. So this is the coordinates of P. So this is the coordinate of P, 2, 1. Okay, and then m tangent here will be f of x naught. X naught is equal to 2 plus h minus f of 2. Okay, f of x naught divided by h. Okay, and then you substitute. Since you are dealing with y equal to 2 divided by x, so f of 2 plus h will be 2 divided by 2 plus h minus 2 divided by 2. F of 2 is 2 divided by 2. It gives you 1. And then you divide with h. And then you simplify this. You got this one. You got negative h. Divide by h, multiply with 2 plus h. Okay. And then as h tends to 0, h and h can be cancelled out. H, if you substitute h equal to 0, it will give you negative 1/2. Negative is from here. Negative 1/2. So that is the tangent, the slope of the tangent line. Okay. So in order to get the equation of the tangent line, you have to substitute y minus y naught is equal to m multiply with x minus x naught. So this is the equation of the line. Okay, so here it is for m. Okay, y minus y naught. In this case, your y naught is 1 and x naught is equal to 2. Okay, x naught is equal to 2. So x minus 2. So this is the equation of the tangent line. Okay. I think you can do example 4 and so on. Okay, it's not too difficult. And then let's go to the velocity. Okay. There's two things when we are talking about velocity. One is instantaneous velocity, and another one is average velocity. The average velocity is dealing with the secant line. So this is the slope of the secant line. Okay. So this is the slope of the secant line. So V average is slope of secant line. Where V instantaneous is the slope of tangent line. So if the questions ask you for the slope, if the questions ask you for the V average, then you have to use the formula for the slope of the secant line. The slope of the secant line is without the limit expressions. Okay, you don't have the limit. But then if the questions ask you for the V instantaneous velocity, then you have to use the slope of the tangent line that have the limit expressions. Okay, so for the V average, it is ft naught plus h minus ft naught divided by h. So this is the second formula, but then without the limit expressions. Before you have like limit h tends to 0 over here. Limit h tends to 0. Limit h tends to 0 is for the instantaneous velocity, not for V average. Okay, so this is the slope of the secant line. I hope it is clear. I don't know how to explain it more details than that. Okay. So for example 5, the questions ask you for of what? Average velocity for the particles over the times interval 0, 2. And for the B, 2, 3. Okay, so for the first one first. Okay, 0, 2 first. Okay, so T naught, our T naught is equal to 0. Our H is the difference. You know that H is equal to T minus T naught, isn't it? Or X minus X naught before you use X. But when we are dealing with velocity, the variable is T instead of X. So here H is T minus T naught. Okay? So our T naught is equal to 0. Our T is equal to 2. So that's why our H is 2. Okay, so the average velocity will be ft naught plus h minus f of t naught divided by h. So f of 2, t naught plus h here, t naught plus h will be t. So our t is 2. So the range is 0, 2. So this is our t, and this is our t naught. The difference between these 2 points is h. So 2 minus 0 is equal to h. So f of 2 minus f of 0 divide by 2. And then 0 is meter. For the our h will be t minus t naught, which means the with our 1. Okay, to 1. Okay, so f of t naught plus h minus f of t naught divided by h. So f of 3 minus f of 2 divided by 1. Okay, f of 3 you substitute in the equations, you get negative 2. F of 2 you get 3. Okay, so negative 2 minus 3 you divide with 1, you get negative 5 meter per second. So that is the average velocity for the second interval, 2, 3. Okay, is it clear? So that is for the average velocity. Okay, okay, now for example 6, the questions ask us for about instantaneous velocity of uh, instead of average velocity. So for the instantaneous velocity, we have to use the formula that involve limits. Okay, that one is for the slope of the tangent line. Okay, for the instantaneous velocity, this is for the slope of the tangent line instead of secant line. Okay, so very slow. Okay. Okay. Okay, and then we have f of t is equal to 1 plus ft minus 2t squared. Okay, and then t is equal to 2, s is equal to 3. So when t is equal to 2, s is equal to 3. Find the particle instantaneous velocity at t equal to 2. Okay, so v average, okay, we are not interested with v average. We want to find the instantaneous velocity. So for the instantaneous velocity, look, if you look at here, you are dealing with the limit expression. So this is the limit expression. So limit h tends to 0. F of t naught plus h minus f of t naught. Okay, f of t naught is equal to, so f of 2. So here t is equal to 2. So f of 2 is equal to 3. So that's why you can write here 3. This one is actually f of 2, sorry, f of 2. This is f of 2. F of 2 is equal to 3, and this part here is for f of 2 plus h. Okay, so this is f of 2 plus h. So 1 plus 5 multiplied with 2 plus h minus 2 plus h squared. Okay, so that's why you got the whole expression, and then you divide with h, and then somehow you simplify this. You simplify all this, okay, and you try to cancel out the denominator. Okay, negative 2 can be cancelled out, I think. Negative 2 plus 10 minus 8, you can cancel out the constant. 5h here, this is 8h, so what is left will be what? So this is negative, so what is left will be negative 3h. Okay, and then here you have negative 2h squared. Okay, so h can be cancelled out. So what is left will be 3, negative 3 minus 2h. Once you substitute h tends to 0, you will get negative 3. Okay, so negative 3 meter per second is the instantaneous velocity at t equal to 2. So this is when at t is equal to 2. Okay, so this is for the instantaneous velocity. Okay, we also have the rates of change. Rate of change and this like before, we know that there's connections between the average velocity and the slope of the secant line. Okay, average velocity, slope of the secant line, slope secant, and then for instantaneous velocity, this is for the slope of the tangent line. Okay, and then if you look at the rate of change, so the difference between rate of change and the velocity is for the rate of change we use the variable x instead of t. For the rate of change we use t. The variable is t because for the velocity we are dealing with time. Okay, we're dealing with time. For the rate of change, we are dealing with the coordinates. So that's why the new coordinates of this one, of the rate of change, will be x, will be the original x, the same like the slope of the secant and the slope of the tangent. So for the rate of change, we also have the average rate of change and instantaneous rate of change. Like before, the average rate of change is dealing with the slope of the secant line. Okay, so this is slope of the secant line, m secant. So this is m secant. And for the instantaneous rate of the rate of change, we have m instantaneous. Slope of sorry, this is not m instantaneous. This should be m tangent. Okay. So m tangent, the slope of the tangent line. So in other words, for the average rate of change, it is similar to the average velocity, and for the instantaneous rate of change, it is similar to the instantaneous velocity. They are the same. The difference is just the coordinates. Like in the velocity, we use t, and this one we use x. That is the only difference. Okay, you can try to do all the exercises. They are just the same. I will leave it for you to do all the example at home. If you have problem, let me know. Okay, they are the same. There's nothing difficult about this, honestly. If you know the theory behind it, it's just the same. So that's it, I think. So it's already 12:30. I think it's better if we stop here. So for the next class, we will start at the derivative functions. Is it okay? Any questions? Anyone want to ask something? Any, Helwit, you want to say something?
If I have a problem with the question, can I personal dokter send at the group?
Sorry?
Macam saya ada masalah, saya mau personal bagi dokter ke macam
You
masalah?
have to discuss with your friends first. You see, In mathematics, you will do a lots of exercises. I've done it before. If all of you, 100 students, cannot solve it, then you can come to me. But it's not a good practice. If you have problem, then you straight away come to me. Okay? If you have problem, please discuss with your friends first. So that is what I've always do. You need rakan sebaya for you to do all the exercises. It's not me to do all the it's not me for to solve all the problems that you have, unless the whole class cannot do it, then you can come to me. Okay, is it okay?
Okay.
It's not that I don't want to solve your problems, but it's not the way we mathematician do the exercises. We have to find our own friends that we can do it together. Okay, and to always discuss it, like 24 hours discuss it. Okay, you better find a very reliable friend, okay, for you to have a very good discussions, okay, before you can come to me. Okay, anyone else? Okay, so that's it. Thank you very much. Okay, I will upload it in my YouTube afterwards. You can check the recorded versions later. By the way, this is already week 4, and there's no more add and drop sessions. Okay, add and drop subject. So I will take the attendance starting next week. Okay. Okay, so that's it. Thank you very much. You can leave the meeting room now.
Thank you, Dr.